Good evening. Oh, let's try that again. Good evening. Thank you. Welcome to Pass the Torch, which is a special lecture series we host here at the Space and Rocket Center when we have amazing, stellar guests, and we certainly have one tonight. How many of you know what the James Webb Telescope is? Everyone does, right? Because you're at space camp, right? We have tonight Dr. Matthew Greenhouse, and he has served as the project scientist on the James Webb Space Telescope since 1997. He specializes in infrared imaging. And the James Webb Telescope is going to be NASA's next great telescope. And it is going to give us a better understanding of the universe and what the universe is made of. It's going to give us a better look back in time, because that's how our space telescopes work. And Dr. Greenhouse has been working with this project for 20 years almost now. He's also, he specializes in instrumentation around infrared observations. His academic background is that he has a Bachelor of Science degree from the University of Arizona, and he has his PhD in physics from the University of Wyoming. He has worked with the Smithsonian Institution, and he has worked at Goddard Space Flight Center since 1996. You're going to learn tonight about the next great instrument we're sending to space. So I'd like for you to give your full attention to Dr. Greenhouse, and at the end of the evening, we'll take some questions. All right? Ladies and gentlemen, Dr. Matthew Greenhouse.
Thank you all for coming. If we could kill the spots, I would appreciate it. Okay. All right, we'll talk tonight about I'll give you an overview of the James Webb Space Telescope mission. The James Webb Space Telescope mission is part of NASA's Cosmic Origins program. And the Cosmic Origins program, as the name suggests, seeks to answer the question, how did we get here? How did we evolve to what we have here today? We've observed the oldest light in the universe with our COBE satellite. We understand what the composition of the universe was then. We have understood now the sort of structure of the universe. We'll talk more about that, but it looks like a big spider web of material. We've looked at old galaxies of all different shapes and sizes. We see that the universe today has a very different composition than it did shortly after formation. We see stars forming around us in interstellar space. We've observed planets around other stars, other solar systems like our own. We've observed planets with water. We have understood the human genome sequence, and we're seeking to complete this picture to understand how life forms in the universe and where life is in the universe. Now, the rate at which we're understanding and answering these questions is increasing at an exponential rate. You all are paying attention to this at just the right time, because things have never been changing faster than they are right now due to the growth of technology. In the old days, astronomers might use pencil and paper and a sketchbook to record what they are observing. Today we have instruments that can extract physics information from starlight called spectroscopy. We can determine what atoms and molecules are producing the light. We've produced a fleet of space telescopes to observe all different colors of light. The JWST will be the newest member of that fleet. Electronic detectors have replaced the pencil and paper sketchbook and replaced our eyes. We don't really use our eyes much anymore in astronomy. We use electronic detectors because the detectors can see more wavelengths of light than our eyes can see, and they're much more sensitive. And so as these technologies, the growth of technology is stimulating discovery at a rate that has never been seen before in human history. Now, traveling back in time is science fiction, but looking back in time is science fact. And what we use telescopes for is to look back in time. That's primarily what the tool is for. So how do we look back in time? Light travels at a finite speed. It takes a certain amount of time to get from one place to another. And so when we look at an object, we see it as it was in the past. If you look at the person seated next to you right now, you're not seeing them as they are. You're seeing them as they were a nanosecond ago. Now, a nanosecond is really small, so we don't perceive that transmission delay. But as we look over larger and larger distances, the delay becomes more noticeable. For example, if we had a magic light switch that if we switched it off, the sun would turn off, we wouldn't know that anything happened for 500 seconds. That's how long it takes for the light to travel from the sun to us. And as we look over larger distances, astronomical distances, we see way back in time. We can see back all the way to the formation of the universe, to the Big Bang. So that's the job that we will do with the James Webb Space Telescope. We built a special telescope called the COBE telescope that was able to observe the oldest light in the universe. The point at which the universe became transparent and photons could escape. The universe was about 300,000 years old, and we've made this image of the universe at that time. These little blobs that you see here are tiny temperature inhomogeneities, and those little temperature changes are what eventually give rise to the whole structure of the universe and the galaxies that we see around us today. We've looked as far back in time as we can with the Hubble Space Telescope, and with Hubble we can see back to a point where the universe was 1 billion years old. But we can't see farther back than that with Hubble because the Hubble telescope is too small and it doesn't have the ability to see infrared light. And so Hubble can only look back to this epoch. So between this epoch and this epoch, there's a mysterious epoch that's never been observed before in the fossil record of the universe called the cosmic dark zone. And the reason that the cosmic dark zone is so interesting to us is this is the period in the history of the universe where the first stars and galaxies formed. A lot of important stuff happened then. We've never been able to observe that epoch before because we've never had the right type of telescope before. And that's what JWST is designed to do. Now, with that Hubble Space Telescope, we stared at a single spot on the sky for a long, long, long time to see as far back in time as the Hubble could see. And when we reach that limit, we have this image, the Hubble Deep Field, and you can see there's a lot more to see after that. We haven't seen the first stars and galaxies yet. And that's because Hubble is too small and it doesn't see the right color of light. Now, when we have JWST flying and we see the first stars and galaxies, we don't mean that you will pick up a newspaper and see a picture of the first galaxy. What we mean is that we will measure the rate at which stars are forming per unit volume in the universe as a function of look-back time, as a function of time back toward the Big Bang. And we will see a precipitous drop-off when we reach the formation epoch, And then we'll know that we've gotten back to the formation epoch of galaxies, and we'll observe many thousands of galaxies at that epoch to really understand them. Now, these error bars that you see here on these data points, they're the uncertainty in the measurement. And you can see as we look farther back in time, the uncertainty is getting really, really big. And that's because we don't have JWST flying yet. But when JWST flies, we will be able to complete that measurement and identify the formation epoch. So when JWST flies, just like HST, we will stare at a single point on the sky for a long, long, long time. But JWST is bigger than HST. It can see fainter objects. And it can see infrared light, which is what one needs to see to observe these first galaxies. And so when we do this experiment with JWST, we expect to see basically all that there is within the wavelength range of the JWST. We will have seen the formation epoch of galaxies and stars. Now, we said the universe has this spider web-like structure. This is a computer simulation of the formation of the universe. So we can give birth to the universe in supercomputers, and now we need to observe the real thing so we know those supercomputer programs are accurate. And we'll just let that run for a while, and you'll see the universe form. While that's happening, let's talk about galaxies. You've all seen pictures of galaxies in textbooks and on posters in your classrooms and so forth. They're very symmetric in shape. Some of them have spiral arms, some of them have bulges, some of them are just big spheres, but they're very symmetric. When we look at galaxies as far back in time as we can with the Hubble Space Telescope, we find that the galaxies way back in the past don't look like that at all. This is 1 billion years after the formation of the universe, and that's closer to today. And you can see that the shapes of galaxies change a lot. And as you go back in time, instead of having these nice regular shapes, they're sort of beaten up, and we call them irregular for lack of a better word. So these are pictures of those irregular galaxies. And we now know today that we can actually simulate the formation of these irregular shapes as a result of galaxy collisions. And we believe that galaxy collisions were more common than they are today in the early universe. And we think that that's the process that causes that change in shape. But JWST will allow us to actually observe that and see what's true. Now, galaxies emit their light, stars emit their light primarily in the ultraviolet portion of the spectrum. Your eyes can't see ultraviolet light, but you can get a sunburn from it. And as that light travels to us, it's traveling across the space which is itself expanding. And so that short wavelength of the ultraviolet light is stretched into the infrared as a result of the expansion in space. So to see it today, one needs to build an infrared telescope. So the infrared capability is necessary for the first galaxies, but it turns out that it's really handy for all kinds of other science that JWST will do. We know that the spaces between stars is not an empty vacuum, the so-called interstellar space. It's filled with giant clouds of gas and dust. And this is where stars are born. This is a famous picture of a giant cloud of molecular gas called the Eagle Nebula. This was taken with the Hubble Space Telescope. And all this brown stuff in the gas is dust, and you can see that it's blocking the light. The reason these clouds of gas are interesting, or one of the reasons, is that this is where stars are born. These giant clouds of gas collapse on themselves due to self-gravity, and as they collapse on themselves, the pressure inside the cloud goes way, way up. Well, what happens when the pressure goes way, way up? It gets hot. When you fill your bicycle tire at the gas station, you can feel it get a little bit hot. Well, in these clouds, it gets really, really hot to the point where nuclear fusion can occur, and that's what causes a star. That's what a star is, and they're born. So we know those basics, but we don't know the details because we can't see through this dust to really get a good look at what's happening inside. But when we look at that same object in the longer wavelength infrared light, you can see right through the dust, and we can get a better view of the star-forming action. So JWST will use its infrared capability to learn a lot about how stars are formed, even in our own galaxy. We know that when stars are formed, there are disks of material, debris disks, that are left over surrounding the star. And those debris disks are very interesting to us because they evolve into planetary systems like our own. This is an artist's conception of the debris disk around our own star. So this debris disk is way outside the orbit of the planets, and this is an actual map of where the debris is. They're called the Kuiper belt objects, or trans-Newtonian objects. And we've put special tracking into the JWST so that we can observe this material in the planets of our own solar system to understand how planets form and how solar systems form. Now, when I was in school, there were no planets known outside of our solar system. No one was sure whether other stars had planets. Today, there are thousands and thousands of planets that are known. This is an image from the Keck telescope in Hawaii, and it's a GIF image, a movie of 7 years of data. And you can see these exoplanets actually orbiting the star in that 7-year period. The star itself is blocked out by an optics component called a coronagraph, and that's because the star is so much brighter than the planets that if we let that light fall on our detector, we would never be able to see the planets. And JWST has coronagraphs like that to observe exoplanets. Now, JWST will not just observe the exoplanets, but obtain spectroscopy of the exoplanet atmospheres and to understand their composition and to look for signs of life, spectroscopic signatures of chemistry that cannot exist abiotically or without life. What do I mean by a spectra? We can look at the light reflected from a planet like the Earth. We can spread that light out into its component colors so that we can see the emission and absorption of individual atoms and molecules. So all these bumps and wiggles in the spectrum are due to atoms and molecules, and we can actually identify them from the bumps and wiggles. So if the Earth had no atmosphere, this would just be a flat line. But it's not a flat line, and that spectra tells us what the Earth's atmosphere is made of. So JWST will be doing this on lots and lots of exoplanets to understand their composition and to look for signs of life. This is a simulated spectrum of a planet like the Earth containing water around another star obtained with JWST. JWST will focus a lot of attention on planets that have water. Why are we interested in water? It's not, it won't go ahead. It's essential for life as we know it, and the thing that makes it essential is not that alien life might get thirsty and need something to drink, but rather for the organic chemistry of life to occur on a planetary scale, we need a solvent available on a planetary scale, and water is what we're most familiar with. We now know that all stars have planets, and that our galaxy has billions of habitable worlds. We don't know, haven't yet found one that's inhabited, but the discovery of extraterrestrial life is imminent. It will definitely happen in your lifetime, probably in mine. So stay tuned. You're born at a great time for being in space camp and getting involved in science and technology. Here's a brief history of our solar system. The solar system is about 4.5 billion years old. And very early in the solar system, it is believed that the Earth collided with another large planet called Theia, and that collision resulted in formation of the moon. The Earth cooled. Maybe it had some water. The orbits of the outer planets switched at one time, destabilizing a lot of debris in the outer solar system, causing lots and lots of meteor impacts on the planets. So when you look at pictures of planets and see planets that are very heavily cratered, they were cratered during this period of late heavy bombardment. It's the so-called Hadean geologic period, about 500 million years after the formation of the Earth. Life formed on the Earth about 3.8 billion years ago. We know that from fossils. It all uses the same genetic code. The sun is continuing to get a little bit brighter as through its normal evolution, so the Earth got progressively warmer. About 300 million years from now, a supercontinent will be produced as plate tectonics proceeds, and another giant supercontinent is formed. About 1 billion years from now, the sun will be 10% brighter than it is now, and it'll be too hot for us to live on the Earth. And then about 8 billion years from now, the sun will run out of the fuel it's burning, turn into something called a red giant, which is much bigger in diameter, and it will actually grow to engulf the Earth. So we have about 8 billion years to find someplace else to live. Luckily, that's, we have plenty of time. All right, when we first put pencil to paper on what do we have to build to do the science I just described, we immediately ran into two big problems that nearly stopped the project. One was that to see those first galaxies, we needed 7 times the light gathering capacity of the Hubble Space Telescope. That requires a mirror that is much bigger in diameter than the biggest rocket. So that was a problem. The other one is that to see that infrared light, we need to make the telescope very cold. Why? Everything above absolute zero emits light. So if we had infrared goggles on right now, we would see the walls and the floor of the room glowing. Our bodies would be glowing. And so if we didn't cool the JWST, it would be blinded by its own infrared self-emission. And to prevent that, we have to make it very, very cold, about 40 degrees above absolute zero, or nearly minus 400 Fahrenheit. So those were two problems that we had to solve, and fortunately we did. Let's talk about the cooling problem first. To get the JWST cold, we aren't going to put it in orbit around the Earth. The Earth is too hot. So we're going to go to a special spot in space called the second Lagrange point of the Sun-Earth system. That's a mouthful, don't worry about that. It's a point in space that's 1 million miles away from the Earth in the anti-sun direction. And it turns out that that spot in space has a couple of special properties that really make it ideal for this mission. We're going to be in a little orbit about that point called a libration point orbit, and so that will cause us to stay out of the shadow of the Earth. We need to be out of the shadow of the Earth because we're generating electricity with solar arrays. But you'll see that in that position, all the sources of heat, the sun, the Earth, and the moon, are in the same direction. So we realized that if we could deploy a giant sunshield so that the telescope would live always in the shadow of the sunshield, it will cool passively to this very low temperature of minus 400 degrees Fahrenheit. Now, we have to stay in the shadow and we have to observe the whole sky. So we solved the problem this way. We sized this sunshade so that we can point the telescope 5 degrees toward the sun, and we're still in the shadow. We can point 45 degrees away from the sun, we're still in the shadow. So now we've observed an arc on the sky that's 50 degrees long. Now you can imagine if we rotate about the Earth-Sun line, so we're rotating about this line, that doesn't spoil our shadow situation at all. And so now this arc turns into an annulus that covers 35% of the sky. So at any moment in time, we could point the telescope at 35% of the sky. Now, as the Earth orbits the Sun, the L2 point, of course, goes with it. So over the course of the year, now we're rotating about this axis. And so one can see that over the course of the year, as we rotate about this axis, this annulus will sweep over the whole sky every 6 months. So every 6 months, we can observe every spot in the sky, always be in the shadow. It's really important that we stay in the shadow because once the JWST gets cold, if the sun ever shines on it, it will break. This L2 point orbit, it's unstable. It has to be maintained with station-keeping thrusters. The propellant for the station-keeping thrusters is an expendable supply that will limit the life of the JWST. So when JWST runs out of gas, if you will, the mission will be over. And so we have it tanked up for about 10 years of operation. So that's how we solve the cooling problem. Now, the L2 point has another tricky property that makes it ideal for JWST. As we orbit the sun, well, if you imagine that if you put a body farther from the sun than the Earth, its period of orbital period around the sun, it would be longer or shorter? Anybody know? Farther away, it would be longer. But the L2 point has a special property that an object placed there will orbit the sun with exactly the same period as the Earth. So by putting JWST there, the telecommunications range to the JWST will remain constant over the whole mission. And that's important for us to get the data back. We're getting the data back by radio transmission. All right, now that mirror larger than the rocket fairing, we had to adopt a segmented mirror architecture so that the mirror could fold up inside the rocket. So the JWST is designed to work with an Ariane 5 rocket, and it has a 5-meter rocket fairing, as this shell of the rocket is called. This is an end view, so you can see that there's not much extra space in there after we fold up the JWST, but it all fits in there, and I'll show you in a moment how that works. This will launch from, this is a French rocket, and it will launch from their launch facility in French Guiana, which is on the east coast of South America. The JWST will be launched warm, and then it will cool off as soon as the sunshade is deployed. It's about 6.5 metric tons. It's a really big satellite. And the origami that you will see in the next slide, the deployment of this involves 40 deployable structures and 178 release mechanisms. Every single one needs to work. Unlike the Hubble Space Telescope, on this mission, if something doesn't work, the astronauts cannot go to the L2 point to save it. So we have to get everything right. Okay, so this is how the unfolding works. The first thing that happens is the solar arrays come out so we can become power positive. We're operating on batteries up to this point. Various correction maneuvers are made to make sure that we're on course to the L2 point. A high-gain antenna comes out so we can begin communicating with the JWST. And these pallet structures that you see unfolding have that giant sunshade folded up inside them. And you'll see how the sunshade is pulled out of them in a minute. An extended mast here provides thermal separation between what will be a very cold telescope and what must remain a room temperature spacecraft. And now you see these telescoping booms pulling the 5-layer sunshade out of that containment structure. And then a mechanism at the periphery separates the 5 layers so that it can perform properly thermally. There are small other thermal radiators that deploy, and soon you'll see the telescope itself begin to deploy. So soon you will see the secondary mirror of the telescope deploying. Okay, that's the secondary mirror. And now the wings of the primary mirror deploy kind of like a round drop leaf kitchen table. And there you have the unfolded JWST. All right, now JWST is the largest science project in US government history. It's about $8 billion to launch. It's too big for NASA to do by itself. So this project is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. The Europeans are providing the launch services, the rocket, and 1.5 science instruments. The Canadians are providing the fine guidance sensor that helps us point the JWST, which is also a science instrument. The operations will occur at the Space Telescope Science Institute in Baltimore, and NASA is doing everything else. It's named after a former NASA administrator from the Apollo era. His name was James Webb. Most facilities like this are named after a famous scientist. This is the first one to be named after a famous administrator. And the reason we did that is that James Webb is largely responsible for there being science at NASA. When NASA was formed, it was very unclear whether NASA was going to do any science at all. You know, it was basically a Cold War geopolitical program. And James Webb really led the charge and insisted that NASA be a science organization. So we felt it fitting to name this after him. This is what the telescope looks like. This is the actual flight JWST in a clean room at Goddard. And this is a full-scale model of the JWST that we take around to talk about the project with people. And you can see from the people standing here how big this thing is. It's really, really a huge, huge satellite. The biggest one we've ever made, you know, other than the station. Now, that segmented primary mirror, there's 18 segments. And so when we first get the JWST up there and we point it at a star, we're going to see 18 stars. And then we need to align each of those 18 segments so that they play together as if they were all just one mirror, one perfect mirror. To do that, we've put some machinery on the back of each of the 18 segments that allows us to adjust it in 7 degrees of freedom. The 6 you may be familiar with, tip and tilt, about several axes, and then we can also adjust the radius of curvature. So with all that adjustment, we are able to superpose all these 18 images into a nearly perfect image. And so that will take place during the first month of the mission. Now, the JWST mirrors, those 18 segments, they're not made of glass. They're made of an element called beryllium. Why did we use beryllium? Well, this mirror is very cold, around 40 degrees Kelvin, and as it slews across the sky, there will be big temperature gradients in the mirror. What happens when you change the temperature of most materials? They expand or contract. And so if we don't hold the temperature of the mirror exactly constant, the shape of the mirror will change. And so we needed to find a material that has a low coefficient of thermal expansion, as they call it, at this operating temperature of 40 Kelvin. And beryllium has that property to a much better degree than glass. And so that's why we chose the beryllium. After we go through the trouble of mining the beryllium, turning it into a big block of metal to make a mirror, we machine almost all the beryllium away, And that's because weight is really a premium in anything that flies. And much of the cost of satellites and rockets and even airplanes comes from lightweighting. And so these are extremely lightweighted mirrors, and they are the lightest mirrors ever produced. They are the state-of-the-art in telescope mirrors. They're 6 times lighter than the Hubble Space Telescope. Now, if you're paying attention, how are mirrors polished? Mirrors are polished by you rub on them with gritty stuff until they get smooth and shiny enough. That's a room temperature operation. We're going to operate this mirror at 40 degrees Kelvin. Materials expand and contract. So this means that we have to put in the wrong shape at room temperature in order to get the right shape at the operating temperature. How do we do that? Well, it's done through the magic of computer modeling, and computer modeling is not perfect. And so we had to polish the mirrors part way. Then we have to put them in a specially instrumented space simulation chamber here at Marshall Space Flight Center so we could cool the mirrors down, look at them with special optics test equipment while they're at 40 degrees Kelvin to see how the actual shape at 40 Kelvin is tracking to our computer model. Then we'd make corrections to the model and send the mirrors back to the polishing house and iterate that procedure until it was finally done. And this is real data, so that's the wrong shape at room temperature, and that's what it turns into when you cool it. And so all this work is behind us now, but it took many, many years to make these mirrors. And the center here, Marshall Space Flight Center, had a very big role to play in doing this testing. The telescope design itself works like this. Light from the star comes in, and it shines, it reflects from that big mirror to that secondary mirror that you saw deploy. And then it goes to a tertiary mirror that you couldn't see, and then to a fourth mirror that is articulated under computer control. That movable fine steering mirror, we use that to remove the blurring effects of vibration that's produced by machinery running in the spacecraft. So that gives us the clear, stable images. Then the light goes to a focal surface where the science instruments reside. And these figures are saying that we did indeed get those mirrors smooth and shiny enough to do the science that we're hoping to do. The structure that holds those mirrors is also a major technology achievement. We could never build the JWST out of something like aluminum. It would be much too heavy. So we had to invent a composite material that could do this job. And the job that the structure needs to do is very complicated. It has to hold those mirrors precisely in shape. It has to withstand 300 degrees of temperature change without distorting. And it has to be strong enough to withstand the launch loads during the rocket flight. And so, but we did come up with a structure design and a material that could do that. Putting this structure together, it involves more than 3,000 pieces that are bonded together in a very, very precise way. And this structure was also thermally tested here at Marshall Space Flight Center. This is just a manual deployment test of that secondary mirror deployment that you saw in the video. And this just gives you an example of some of the kinds of testing and activities that occur in the clean room. And this video shows how we put the mirrors on the backplane. This is a robotic pick-and-place machine. It has a robotic arm with a high-precision end effector that allows us to precisely place these mirrors for integration onto the backplane. These mirrors, these are the actual flight mirrors, they have black covers on them to keep them clean, but underneath those black covers are the gold-coated mirrors. So you get the idea of how this works. This is a typical handling operation of of the JWST in the clean room at Goddard. Gives you just a sense of what it's like working with this thing and handling it. This is the actual flight telescope, and here we're just putting it on a turnover fixture to do some work on it. That's the real thing. Okay, let's talk about that sunshield for a minute. This is one of the more difficult parts of the JWST. The sunshield has an SPF of 1,000,000. So if you had this thing on the beach, you would be very, very well protected. It is literally the size of a tennis court, 70 by 40 feet. It has 5 layers. It's made of a material called kapton. Each layer is thinner than a human hair. Each layer is coated with vacuum-deposited aluminum. The sunward-facing layer also has a silicon deposited on it to help it withstand the solar radiation for 10 years. So it actually looks pink in real life because of that silicon coating. It has a precise curved shape to prevent light from reflecting off the sunshade and getting into the telescope. Those of you who may sew for a hobby know that you can't make a curve out of flat cloth without seams. Each one of these layers is a quilt of more than 50 pieces. And each of those pieces are seamed together not with needle and thread, but with thermal spot welds. 7,000 inches of thermal spot welds. So building this sunshade was a really tough job. It was done here at a company called Nexol, right in your backyard. And it's a major technical achievement, and it's a very critical part of JWST. This is a manual walkout deployment test of that sunshield. These tables are providing gravity offloading. And here we're practicing how to fold the sunshade up in that containment structure. This ground support equipment that's pulling it out is standing in for those telescoping booms that you saw in the deployment animation. And if you pay attention, you'll see a person appear in the hole in the center here periodically, and that gives you a sense of how big this thing is. And you can actually see the quilting here. Okay, you get the idea. Okay, let's talk a little bit about the science instruments that are on the business end of the telescope. This big primary mirror, the thing we call the telescope, its job is to collect the light from the very faint objects that we're observing, sends that light to the instruments. The instruments process the light a little bit, convert it to digitize the light, convert it to ones and zeros, send it back to the Earth so that we can extract the physics information that the light contains. This is the main infrared camera on the JWST. This is the one that will see the earliest, the first stars and galaxies. It's actually 2 cameras, 2 redundant cameras, and this whole thing is made of beryllium, and it uses lenses, which is also unusual in the infrared. This is the main spectrometer on the JWST. It's a very unusual instrument. This whole thing is made of an advanced ceramic material called silicon carbide. And so the whole thing is held together with friction. And it's also a spectrometer that can target and obtain spectra of 100 objects simultaneously, keep all those spectra separate. And we had to build this instrument with that capability because those first galaxies are very, very faint. We have to stare at them for a long, long time to obtain a spectrum, and if we tried to observe them one at a time, we would never get enough of them observed during the life of the mission. This is the mid-infrared instrument on JWST. This is a camera that works way out in the infrared, a wavelength of 5 to about 30 microns. And this one will give humanity its very first high-definition view of the mid-infrared universe. We have never had an ability to see the universe in the mid-infrared with the angular resolution, the ability to see fine detail that JWST and Hubble have. And so this will be a very important instrument on JWST. And this is the Canadian instrument. It's a fine guidance sensor that can sense pointing to a millionth of a degree. And it is also a science instrument that will be obtaining the spectra of those exoplanet atmospheres to look for life and other chemical composition. This is what the instruments look like when they're all packaged up into a module that goes on the back of the telescope. And that's the actual flight instrument package. And that is all completed now, and it's integrated with the telescope now, and that's the actual flight thing. Now, to test that instrument module, we had to use the biggest space simulation chamber at Goddard, and even that big chamber is not big enough to put the telescope in. So we had to test the instrument module in this configuration where it's looking down on a simulator of the JWST telescope. So this is an optics assembly that produces a high fidelity simulation of the JWST telescope beam. And this chamber has shrouds that are cooled by liquid nitrogen and liquid helium, so we could simulate the cold and the vacuum of space. So this can operate at its expected temperature of about 40 Kelvin. And this is a picture of what the lower area of this chamber happened to look like in one of these tests. And so you can see these are very complicated, difficult tests. These are the most difficult cryogenic tests the agency has ever done. We've had to test that instrument module 3 times, each time for 100 days, operating 24/7. All that's behind us now, and the instrument module's in great shape. With the instrument module attached to the telescope and folded up, we put it into a special shipping container that is truck mounted, and that shipping container gives the JWST all the special environment that it needs to stay healthy and safe. And we've designed this to fit inside a C-5 transport aircraft. There are only 3 physical aircraft in the fleet that can carry this particular payload. It fits in there. It's a pretty tight fit, as you can see here, but it does fit. And we use this technique to fly it from Andrews Air Force Base near Goddard Space Flight Center down to Houston, Texas, to do more testing in the largest space simulation chamber in the world at Johnson Space Flight Center called Chamber A. Chamber A is a remnant of the Apollo program, and we had to pull it out of mothballs and completely refurbish it for JWST. This is a picture of the door of Chamber A, and that's the Apollo command module inside there. This is actually a man-rated chamber, and during Apollo, there were astronauts inside here. We're not sending anyone in the chamber, but we've refurbished this and designed it so that JWST could roll through this enormous door into the chamber and then be suspended from the top of the chamber on rods and look at special optics test equipment in the top of the chamber to do what's called an end-to-end optical test. The mental image that you might form when you hear end-to-end optical test is exactly the right image. We're going to shine light through the telescope just the way it will happen on orbit and have it go through the whole system, through all the instruments, and we'll see everything works perfectly. That's a very difficult test to do. It's a test that we did not do on the Hubble Space Telescope program with consequences that I think many of you are aware of. We have to get JWST right because the astronauts can't go to the L2 point, so we're not skipping this test on the JWST program, but it was a very, very difficult test to do. It took us many, many years to get this chamber refurbished, and all this work is behind us now. This testing occurred this past summer. This is a picture of JWST, the actual flight article, in Chamber A, getting ready for that test. When we finished that test this past October, we went back into the aircraft and flew to Los Angeles, California, to Northrop Grumman Aerospace Systems, and where we will be joining the telescope and its instruments to the spacecraft bus and this sunshield. So that's what we're working on as we speak. This is what the clean room at Northrop looked like a few days ago. And let me talk about what we're looking at here. So this is the final JWST assembly. That's a CAD, cartoon. And so that is these two pieces joined together. These long pink things are the sunshade containment structure. The sunshade's actually in there, and the spacecraft bus is down here. All this pink stuff is flight hardware. The silver stuff in the middle is a mass simulator that's simulating the real telescope. So right now, as we're speaking, this assembly is undergoing acoustic and vibration testing. We have to shake it to simulate the vibration of the rocket flight, and we also have to blast it with giant loudspeakers to simulate the sound that occurs inside the rocket. When we come out of that test in a few days, then we have to deploy the sunshield so that we know it survived the test okay. After we deploy it, we have to fold it all back up again. That takes 45 days just to do that. Then we will remove this mass simulator and put the real thing in its place to form that. Then we have to go back into that acoustic vibration test to show that this thing is all okay. Then we have to deploy the sunshield again and fold it up again, and then we ship to the launch site. So we're at the very end of the program right now, putting the last two pieces together. It's very slow and time-consuming to do that, because at this point in the program, all we care about is doing it right and making sure that everything works. We don't cut corners because of cost or schedule pressure. But that's where we are now. When we finish that, when we have the spacecraft and the sunshield, those two pieces joined together, now it's too big to fit in the C-5 aircraft. And so we are going to roll a slightly larger shipping container like this onto what's called a roll-on, roll-off transport ship. And we will depart from Port of Los Angeles. We'll go through the Panama Canal over to French Guiana, where we'll roll off the ship and onto the, into the launch complex. That journey will take us about 20 days to get there.
The efforts of thousands of people across the United States, Canada, and Europe for almost 2 decades achieved this milestone. The optical and science segment of the largest space telescope ever constructed stands complete in one of the largest clean rooms in the world, ready to endure its toughest yet battery of testing. Getting to this point wasn't easy. Never mind the logistic and construction challenges this international endeavor presents. Before astrophysicists' dreams of building Webb could be realized, 10 technologies that did not exist needed to be created and perfected. They were. To give you a sense of where we are in the mission, the Webb telescope consists of 3 main segments: the spacecraft bus, the sunshield, and the telescope, which includes Webb's instruments. This telescope segment of NASA's most ambitious space observatory stands complete and tall in the NASA Goddard Space Flight Center clean room. An international team of engineers built and tested this revolutionary telescope segment. Beyond spaceflight hardware, the Webb mission required building assembly structures, test facilities, transportation enclosures, engineering copies called pathfinders, and even a miniature test-bed telescope. Revolutionary, lightweight composite material capable of maintaining its shape to 1/10,000th of a human hair at temperatures near absolute zero forms Webb's backplane and science instrument support structures. Webb's mirror segments began as beryllium ore mined in Utah. They crisscrossed the United States to be formed. Lightweighted, polished, gold-coated, and finally, perfectly placed on the backplane structure with the help of a robotic arm. 4 state-of-the-art science instruments from NASA and its international partners, the European Space Agency and Canadian Space Agency, were installed and tested, each loaded with advanced components and detectors, and capable of operating at temperatures near absolute zero. Scientists will use these instruments to tease out answers to astronomical mysteries near the edge of the visible universe, in galaxies closer to home, around planets orbiting our star, and others like it nearby. The Webb telescope segment now stands complete. After launch phase environment testing at Goddard, this segment will endure more cryogenic testing at the NASA Johnson Space Center. Later, the telescope will travel to Northrop Grumman in Los Angeles to be mated to its sunshield and spacecraft bus, thus completing the observatory's assembly. The James Webb Space Telescope, our new eye on the universe.
All right, well, we're not going to answer all the questions with this mission. There's still plenty for you guys to answer. In your generation, what happened before the Big Bang, what's at the center of a black hole. Your generation will figure that out after we get the JWST working. But I really want to leave you with an understanding that growing up to build spaceships, to build rockets, to do astrophysics and all this engineering, that's something that every one of you in the audience can do. Projects like this involve every kind of person from every walk of life. And they do have one thing in common. And I want to read this quote from Galileo. "The book of nature lies continuously open before our eyes. But it can't be understood without first learning to understand the language and characters in which it is written. It is written in mathematical language, and its characters are geometrical figures." That's as true today as it was 400 years ago when Galileo said it. Go to college, study science, engineering, and math. Doesn't matter what kind of science or what kind of engineering. Just follow your heart and go to college and study that. Every discipline of engineering that exists has a role to play in projects like this. Biologists are involved, even lawyers are involved. So whatever you want, whatever strikes your fancy to study in college, just go off and study it and know that the people that do projects like this are just like you and you can be one of them. So that's what we have to say, and if you want to follow JWST, the remaining development to launch and beyond, just follow us on Twitter @NASAWeb, #JWST. And thank you for coming out tonight.